Hello, everybody. This is Mr. Page speaking. If you go ahead and take out your packet and open to the Dihybrid Crosses page, I'm going to go through the notes with you on this. If you have not seen the monohybrid crosses, you probably should watch that first. Before we jump into the actual notes, I'm going to talk to you a little bit about the 3 laws of genetics that Mendel kind of came up with his experiments with pea plants. The first one is a law of dominance, which simply states that one type or allele, one variation of a trait can dominate over another, such as yellow peas dominating over green peas. The other one is the law of segregation of alleles, and this is the idea that you get one allele from one parent and the other allele from another parent, and so that you are a diploid organism. You have 2 sets of all your traits, one coming from each parent. And that's the law of segregation, which Mendel came up with. And the third law that he came up with when he was studying 2 traits in one cross was the law of independent assortment. And the law of independent assortment really, kind of in layman's terms, just means that you inherit one chromosome from mother and one chromosome from father, and that because of that, if you get a chromosome number, put it this way, if you get a chromosome number 1 from your father, doesn't mean that chromosome number 2 has to come from your father. It very well might come from your mother. So you get one chromosome from each parent, and one pair of chromosomes does not influence the other pair of chromosomes. And the way he figured this out was when he took 2 traits and he crossed them together. So what he identified was that 2 or more pairs of genes segregate independently from one another during gamete formation. And that support that he has from that was the support from his experiments with pea plants with 2 or more contrasting traits. So actually Mendel got really lucky with this in that he studied traits that happened to be on different chromosomes. He obviously didn't know this at the time, and his experiments would not have been as successful if he had chosen traits that were on the same chromosome, but he's able to kind of get these underlying very basic laws of genetics by studying these simple pea plants, which happen to have these traits on different chromosomes. So in a nutshell, Mendel was really lucky with his experiments. So the idea, or how he came up with this third law of genetics, this law of independent assortment, came with the crossing of 2 different traits at one time. And so what he initially did is he took some plants that were purebreds, that were pure lines, for yellow seeds and yellow round seeds, so a big Y, big Y, big R, and some that were pure lines for the recessive traits, little y, little r, little r. And what he found out in the F1 generation, phenotypically, every single one of them would be yellow and round. Yellow peas that are round, every single time. And genotypically, what he was forming was this. He was getting individuals that were heterozygous for both those traits. In the F2s, he would do this over and over and over again, so he had just huge amounts of numbers and data with this, but it could be always boiled down to this, that the F2 generation would get 9 yellow round individual plants. He would have 3 yellow wrinkled, 3 green round, and then a measly 1 green wrinkled that would have both recessive traits again. And so he would do this, but the ratios could be boiled down to that, 9 to 3 to 3 to 1. where the dominant trait was the most oftenly expressed And the ones that had one dominant trait were the next ones, and the ones that had the recessive traits, well, they were few and far between. So what he concluded was this. Now, this is a great experiment, a great set of experiments using inference. He get all this data, and he had to make sense of it. And so he had to infer what was going on at the gene level. And he amazingly was right. So in the P generation, he already had that idea of the law of segregation of alleles. And so what he thought was, well, in those P generations, they're making sex cells that happen to actually be all the same because of their pure lines. So you can see on this individual, you're going to get all big Y, big R. In this individual, the only way to pair it up will be little y with little r. And so that way, he could make sense that he could get all yellow round, because what would end up is all the babies would have that big Y that's masking the little y, and have a big R, which is masking the little r. And so he can make sense of that. Then he thought, well, if I take those F2s, the F1s to make my F2 generation, well, I gotta do something a little tricky with these, because there's the capital ones and the lowercase ones, and so what you can do is actually FOIL it. You guys are familiar with this from math, first outside, inside, last, and so that's what you can do here. Take your first ones, big Y, big R, your outside ones, big Y, little r, the inside ones, little y, big R, and the last ones are little y, little r. And the same thing over here for the other parent. Now, it doesn't really matter here which is the male, which is the female, because they're both making the exact same gametes. So we could say this is the female, and over here is the male, and we can go ahead and get our F2 generation. Now, you notice here our Punnett square is a bit larger than we're used to. It's a 4x4, so 16 possibilities here for the genotypes. And so what I want you to do is you can go ahead and fill this in, either with me, or you can jump ahead and fill them all in. And then after I get these all filled in, what we're going to do is we're going to go through and think about the genotypes that Mendel would have seen. Okay, so what I'm going to do is I'm first going to count out all the yellow round ones, and I'm going to highlight those in yellow. So these will be individuals that have a big Y and a big R. So I'm just going to go through looking for big Y, big R's, big Y, big R's, big Y, big R's. I'm just going to go ahead and highlight those. And so what I come up with here, if we count 1, 2, 3, 4, 5, 6, 7, 8, 9 are the round yellow plants. Next, I'm going to go ahead and do the greens, and we'll make the green, we'll go with green round. So these individuals are going to be little y with a big R. So little y with a big R. And there we have it. There's only 3 of those. Next, we're going to look at yellow, wrinkle. We'll highlight these guys in blue. There we go. And so these guys would be a big Y with 2 little R's. And there are 3 of those. And the last one's going to be our green wrinkled. And we're going to do that one in purple. And we can see that there's only 1 of those. And so we get Mendel's 9 to 3 to 3 to 1. Phenotypic ratio. Now note, this is only true if they're on different chromosomes. As I mentioned before, Mendel was very lucky with his experiments. This would not have worked if the genes happened to be on the same chromosome, and we will talk about that later on in the unit with linked genes. So that's all for today.